Hello, Physics 11, and welcome back to our online course videos. Today we are going to start off our next unit. We're going to start talking about forces and Newton's laws. We're going to spread this forces unit out over two separate units. The first one is going to be the introduction to forces and the Newton's laws, and then we'll get more complex in the next unit dealing with these dynamics, as we call it, for the overall grouping of these. All right. First off, we want to talk about force. And in terms of force in physics, we are talking about any sort of a push or pull. Okay, so we usually talk about the force of gravity as being one of these ones, and that's probably the one that we're going to talk about most in this course. And that is that pull of gravity, right? We've got to be careful here. We talk about the units of force. Okay, our units of force, we use newtons, okay, in honor of Sir Isaac Newton. Okay, and we give those the symbol capital N. Okay, now in terms of what these actual units are, it is going to be kilogram times meters divided by seconds squared. Okay, we'll see that in the a little bit further on here where we actually get those. But for units of force, we're going to talk about newtons. All right. Next up, we want to talk about the different types. There are four fundamental forces. So the first one we're going to talk about here is gravitational. All right, so we got gravitational force. And that's the one we're going to be dealing with in this course here, as well as possibly like an actual physical push or pull. Okay, but we're going to start off talking about the gravitational force. We also have the electromagnetic force. Force. Okay, we're not really going to deal with that one too much in this course. However, it does come up in in Physics 12. Okay, and then the other two are the strong nuclear force and the weak nuclear force. Okay, so strong nuclear and the weak nuclear. Okay, we're not really going to touch with these too much, but for those of you that are interested, the strong nuclear force is what keeps all those positive protons stuck together inside of a nucleus, and the weak nuclear force is used in nuclear decay and radioactivity. All right, continuing on, we've got the force of gravity. Like I said, that's going to be the main one we're going to talk about for this course. So, force of gravity, this attracts all matter to other matter. So essentially, if you are matter, you've got mass, and if you have mass, you will be attracted to each other based on this force of gravity. Okay. Now, we always see these mass and weight, and usually up until now, we've considered those to be the same, but they are in fact very different. Okay. So mass. Let's switch colors here. Okay. This is the amount of matter an object is made of. Okay, so mass is the amount of matter, and it has those units kilograms. Whereas weight, okay, as you'll see here, I've got that written down as the force of newtons, or the unit of newtons, okay, and that is because weight is the force of gravitational pull. Okay, so we've got mass is the amount of matter in an object. However, weight is the force of gravitational pull on that object. Okay, so what we should say here is that mass is constant, okay, throughout the universe, but weight changes depending on where you are and what your gravitational pull is. All right, since we're mostly talking about the force of gravity, okay, we're going to look at this F sub g, right? We're going to use this F for our force, and since we're talking about gravity, we're going to say the F sub g, okay, the force of gravity, is equal to the mass of the object multiplied by the gravity. Okay, so what we have here then is this F sub g is the force of gravity. M is the mass of the object. Being sure to use that in kilograms. Okay, and then we have our G. This is the acceleration due to gravity. Okay, and we've already been using this force quite a bit, or this acceleration due to gravity, and so just remember that for where we are on planet Earth, we're going to talk about gravity as being that negative 9.81 meters per second squared, or we say that 9.81 meters per second squared. Directional depends on you, okay? And so when we were talking about our force previously, and we said that newtons were kilograms times meters per second squared, well, this is why. If we're taking mass times gravity, and gravity has that units of meters per second squared, and mass has those units of kilograms, this gives us kilograms times meters per second squared as the units for force, or for newtons. All right. Now, I said we got this G, and we're going to use that 9.81 meters per second squared for here on Earth. However, G varies depending on where we are, right? And so we talked about how your weight can change depending on where you are. Well, that's because the force of gravity, or the gravitational acceleration, is going to change depending on where you are. And so that G depends on two different things, okay? And the first one is the mass of the planet. Okay, so the first one we want to talk about is the mass of the planet. The second one that we're going to deal with is I'm going to talk about the distance to the planet if we're talking about say the force of gravity, or the value of gravity from the sun to the planet. Or if we're talking about an object on the planet, we're going to talk about the radius of the planet. Okay, so the mass of the planet, and then the distance to, or the radius of that planet, depending on if we're far away from it or if we're actually standing on the surface of that planet. So, for example, we're looking at on Earth, and specifically here we're talking about at sea level. We're talking that our gravity here is that 9.81 meters per second squared that we've been dealing with. However, if we look at the moon, and we saw this in that last test, that the moon has a gravity 1/6 that of Earth, and so we said it is approximately 1.6 meters per second squared. Okay, if we go to a planet larger than Earth, let's talk about Jupiter, our largest planet. In this case, we get a G that is approximately 24.5 meters per second squared. 24.9, 24.5, somewhere in that range. Okay. And then if we were talking about being on the surface of the sun, obviously something that we couldn't possibly do, but we would have a gravity here of approximately 274 meters per second squared, or an acceleration due to gravity at that level. Okay, so we can see the different mass, the different radius of these different objects that we're talking about has a huge impact on the different varying values of gravity, or acceleration due to gravity, I should say. Okay, if we look at that next example, and this is going to be very similar to your next activity that you're going to deal with as well, but first off, let's take a look at your mass. Okay, and for now, we're just going to take a simple assumption that approximately 100 kilograms. Okay, probably bigger than most of you, probably all of you, but let's just use this nice easy number to figure this out. All right, so that is our mass, but we want to find our weight. Okay, so if we're looking at our weight, let's take a look at a couple different options here, right? So if we're looking at Earth, right, we are going to say that our weight here, Fg equals m times g, okay? And so we have 100 times that 9.81 gives us a value of 981 newtons here on Earth. Okay. If we took that same mass of 100 kilograms and we went to the moon, our formula is the same, mass times gravity. However, this time our mass stays the same. Our gravity changes to that 1.6 meters per second squared, and this gives us a weight of 160 newtons. Okay, and once again, similar process here. If we take a look at Jupiter, again, our mass stays the same, right? We have that same amount of mass everywhere we go. So our mass stays the same, and then this time our gravity changes to that value of the 24.5, and this gives us a weight of 2,450 newtons. Okay? Now, hopefully that helps understand a little bit how your mass is the same no matter where you go, but your weight can change depending on where you are. Okay, so hopefully that helps. Next up that I have there for you is that little activity, trying to figure out how high you could jump on the surfaces of the moon. And what was once the sun, I've changed to be Jupiter. Okay, so make sure you take a look at those. Now, what you're going to do is you're going to use your kinematics formulas. Okay, so if we know our height that we can jump, so if you have a family member measure the height you can jump, right, you're going to get your dy, right? You're going to get your vertical distance. For simplicity's sake, let's say that we can jump 0.50 meters, a half a meter, right? Okay, 50 centimeters. A very high vertical jump, but that's okay. Now, using this and our formula that dy equals, let's use vf squared equals vi squared plus 2ad, where this a that's inside here is at first our acceleration due to gravity of 9.81, and we know at the peak of our jump this goes to 0. We can find that initial velocity. Okay, now Similar process. You're going to take this and you're going to figure out your how high you can jump on the moon and on Jupiter using that same initial velocity. We'll assume that that's the same everywhere you go. Figure out how high you can jump, right? You'll use the same initial velocity from here on Earth. You'll use whatever the acceleration is on the moon or Jupiter as given to you, and use that to calculate the distance. Once you have that, you can use your other formula of dy equals vit plus 1/2 at squared. You can then figure out your hang time, or how long you can hang or you stay in the air. Alternatively, that is a little bit more complex of a formula. You could use the vf equals vi plus at, making sure that you pay attention to which acceleration you're using based on those different planets. Okay. Hopefully that helps with your little activity. Please make sure you have that finished and post your answers in the discussion that is available for you on Schoology. Okay. Next up, we just want to talk a little about g-forces. Okay, g-forces are actually a measurement of acceleration experienced by an object. So we usually talk about g-forces when we're talking about race cars or jets. Okay, so when you're at rest on Earth, you are experiencing just 1 g. Okay, so you have that one gravity pulling you down. However, if you're accelerating upwards in a plane or a rocket, or if you take a sharp corner, you're going to experience that acceleration on the on here as well. So, since we have this 1 g equals 9.81 meters per second squared, okay, we can say that if a car accelerates at 4.9 meters per second, okay, what we'd want to do is we would say if 1g equals this, we can take this 4.9 meters per second squared multiplied by 1g that has that value of 9.81 meters per second squared. This gives us approximately 0.5 g's. Okay, so if you're in a car that's accelerating at 4.9 meters per second squared, you would feel a 0.5 g of force. Okay. If we're talking about a shuttlecraft or a rocket that's launching and has an acceleration of about 28 meters per second squared, okay, we can do that again. We can take that 28 meters per second squared times by 1g over that value of 9.1 meters per second squared. Now this is just so that those units cancel out and we get into that g. And for this one, we have a value of approximately 2.9 g's. Okay, so a shuttle launching off would feel approximately 2.9 g's of force. Okay. Last little example we have here on g's. A normal person can experience or can withstand 4 g's before they pass out, while a fighter pilot can withstand up to 9 g's of force. So we want to take a look and see what accelerations would cause these people to pass out. So for a normal person, okay, we are looking at 4.0 g's multiplied by that 9.81 meters per second squared for every 1 g. Okay, and so when we multiply those out, we get 39.24 meters per second squared. Okay. Whereas if we're looking at a fighter pilot who has gone through rigorous training to be able to accommodate these higher g forces of the 9.0, they also have their suits that help them out with that. We can take that 9.0 g's that they can handle, we multiply that by that 9.81 meters per second squared for every 1 g. And we see that a fighter pilot can withstand an acceleration of 88.29 meters per second squared. Okay, so nice, easy calculations to solve these different g-forces and to help figure out the force of gravity. All right, after our introduction to forces, I mentioned we're also going to start talking about Newton's first law. This is also known as the law of inertia. Okay, but simply this law states that an object in motion will stay in motion, and an object at rest will stay at rest unless acted upon by an external force. Now I'm going to say an external net force. Okay, so some sort of an unbalanced force will cause this to happen. So essentially we're saying an object in motion will stay in motion, or an object at rest will stay at rest unless it is acted upon by an external net force. So an object will not change its motion or its state of rest unless it is pushed or pulled by some sort of object acting upon it. Okay. Now I said that this is also, so hopefully that makes sense. Also we have this law of inertia. Okay. Well, inertia is how difficult it is to change an object's motion. Okay, so how inertia, the law of inertia is just how difficult it is to change an object's mass, an object's motion, and this is related or proportional to the mass of that object. Okay, so how difficult it is to change an object's motion. Now, we're talking about the example we have here at the side is, imagine you're racing around a track on a go-kart. When are the 3 times you would notice inertia? Well, the first time we're going to notice inertia is when we start accelerating. So when we are starting the race. So starting our race, or when we are speeding up. Okay, we'll notice that inertia. If we slam on the gas, not that it's very fast, but we'll notice that we'll feel that push back against us. The second time we notice inertia is when we are turning around a corner. Okay. We were going straight, we're changing our motion as we're moving around that corner. So we're gonna, if I'm going this way around a corner, I'm gonna feel that inertia pushing me out on that side. Okay, this is where we get that that thrill of being in a different type of ride at the P&E or at the fair. Okay, and the third time that we would experience inertia is when we are stopping, okay, or braking, slowing down. Okay, we're going to feel that change in our velocity as we're moving, right? So anytime we see these 3 situations, we are experiencing inertia, okay, a change in our motion. Okay, so just another way of thinking of that Newton's first law is that if there is no net force on an object, then it will stay at its constant velocity, right? And remember, velocity is a vector, so any change in the direction is a change in that velocity. Okay, so we got to be careful with that one when we're thinking about these. Any change in direction is going to experience that inertia. Okay. Also, if an object is not moving, then we would have a constant velocity of 0. right? So, and again, any change in that velocities. So an object in motion will stay in motion. An object at rest will stay at rest unless they are acted upon by an external net force. Okay, just a couple examples here. Imagine a book sitting on a table. Okay, so we have our book sitting on the table here, okay? So now we have this force of gravity pulling down on the book. Okay, so we would have this force of gravity pulling down. But at the same time, this object's not moving because it's sitting on the table, and the table is exerting what is known as the Fn, or the normal force. Okay, force of gravity is pulling this book down, the table is pushing it back up. They stay at the same value, it's not actually moving. So we've got the force of gravity pulling it down, and we have the normal force holding it in place. Okay, now if we were to all of a sudden get rid of this table and all we had was our book, and let's say we're dropping it from a height, well, we have an unbalanced force here because we've just let it go, and so the only force we have acting on it right now is the force of gravity, which means that the book accelerates towards the ground. Okay, so in the first situation we had the table holding the book up, it had that normal force, whereas in this situation we've removed anything to hold it, and it's just the force of gravity, and so it is accelerating. Okay, as you notice, there's a few other examples down there at the bottom. Hopefully this helps your understanding of the difference between mass and weight, the force of gravity, and Newton's first law.